Vision IB, where physics becomes clarity.
My dear student, welcome to the 7th lecture of thermodynamics. In this session, we are going to discuss the numericals of thermodynamics. So let's begin with the first numerical. So here we have an isothermal change of gas at 63 degrees Celsius occurs by transferring heat of 3360 joules of heat energy to the surrounding medium. What is the change in entropy of the gas during this process? So we have to calculate the change in entropy of the gas during this process, right? So we have the formula for change in entropy as delta S equals delta Q by delta T. So if we name this, we know that delta S is entropy, delta Q is heat, and delta T is temperature. Now we know that delta S is equals to delta Q by delta T. But before solving this numerical, we have to convert Celsius into Kelvin. So we have the conversion of Celsius into Kelvin, which can be written as temperature in Kelvin is equals to temperature in degree Celsius plus 273. So after this, just let's start with our numerical. So as we know that delta S is entropy, delta Q is heat, and delta T is temperature. Now since it's an isothermal gas at 63 degrees Celsius, so now we have delta Q, that is 3360 joules. So delta Q can be written as minus 3360 joules, while delta T is change in temperature. So temperature is given to be 63 degrees Celsius, so it will be 63.0 plus 273. So we have to convert joules into Kelvin. The relation is given here. So now we can write this equation as, so after we solve this, we get delta S, that is change in entropy, as minus 10.0 joules per Kelvin. So from this equation below, we can see that the change in entropy is given by minus 10 joules per Kelvin, right? So why there is a negative sign? So you must be wondering why there is a negative uh, sign in the heat energy. So it's an isothermal process and change isothermal process at 60 degrees Celsius. So heat is transferred in this process. So since the heat is transferred in this process, that's why we have negative sign here. So hope you understood the why we took the negative sign here of change in heat. So based on this calculation, we have change in entropy as minus 10.0 joules per Kelvin. So the correct answer is B. So let's begin with the question number 2. So in this question, what this question says is, in this question, the work done when 1 mole of gas expands through an adiabatic process of 120 joule. We need to calculate what is the change in the temperature of the gas, right? So you are very aware that the adiabatic process, no heat transfer takes place between system and surrounding. So I hope adiabatic process is clear. Now we will be using two equations to solve for the change in temperature of the gas. So we know that delta U is equals to Q minus W. So what is delta U? Delta U is internal energy. Internal energy. What is Q? Q is the heat. And what is W? W is work done. Now we have one more equation for finding U, that is internal energy. That is U is given by 3 by 2 N times RT. So what is N? N is number of moles. Number of moles. What is R? R is gas constant. And what is T? T is temperature. Right? So we will be using these two equations to find the change in the temperature of the gas, right? Now, we are very much aware that ideal gas constant, that is R, is equals to 8.31 joules per Kelvin per mole, right? So we have to use this data while solving the numeric. So we already know that for an adiabatic process, delta Q is equals to 0. It means there is no heat transfer between the system and the surrounding. So if we use this equation of change in internal energy, so the change in internal energy, that is delta U, is given by 0 minus 120 joules. So work done is, so gas expands during the adiabatic process and the work done is 120 joules. So we have change in internal energy, that is delta U equals to minus 120 joules. Now let's jump to the second part of the problem, which also says that delta U equals 3 by 2 NR delta T, where we know that N is number of moles, R is the gas constant, and T is the temperature. Now let's substitute these values and see what do we get. So we already know that change in internal energy is 120 joules divided by, which is equals to 3 by 2. And we have 1 mole of gas. So N can be written as 1. The value of R can be taken as 8.31 joules. And the value of, we have to find the change in temperature, that is delta T. If we rearrange this equation, we get delta T as 2 times minus 120 divided by 3 times 8.31, which gives us the value of minus 9.6 Kelvin. So from this, it is clear that the correct answer is minus 9.6 Kelvin. Hope you understood this numerical. So my dear friends, we have one more numerical. We have a monoatomic gas. The volume of the monoatomic gas is 1 centimeter cube. The pressure is 1.0 HPa. Now you must be wondering what is HPa. HPa means hectopascal, which expands through an adiabatic process to 8 centimeter cube. We have to find the final pressure of the gas in hectopascal. So we have the equation to solve, to find the pressure of a gas in hectopascal. So we have an equation for that, which is given by P times volume raised to 5 by 3, which is equals to constant. Now Let's define the terms. So here P indicates pressure, while V indicates volume, and this is constant as you are aware. So now let's uh, equate and solve this equation, solve this numericals. So we have to find the pressure P2, the final pressure in hectopascal. So if we write this equation, we can write it as P1 V1 raised to 5 by 3 is equals to P2 V2 raised to 5 by 3. Now, as we solve it further, if we just arrange this equation, we have to find the value of this P2. So we will just rearrange this equation and write it in the simple form where you can find the P2. So P2 may be given as P1 times V1 by V2 raised to 5 by 3. Hope you are not getting confused with this. It is a basic calculation part, basic law of indices and algebra. So hope you are understanding this and you are on the same path as I am teaching you. So we know that the pressure is given as P1 is given as 1.0 times. We know that the V1 is given to be 1.0 HPA times V2 is given as 8.0 raised to 5 by 3. Now if we solve this further, we get it as 1 by 8 raised to 5 by 3, which can be written in the simplest form as 1 by 2 raised to 5. If we calculate this, we get the final pressure, that is P2, as 1 by 32. So it is clear from the solution that option A is the correct answer for this question. So the final pressure of the gas in HPA is 1 by 32. So my dear friends, we have one more numerical. So in this numerical, there is a pressure volume diagram. It's a pressure volume diagram. So we have pressure on y-axis and volume on x-axis. So it shows the pressure volume diagram below shows the cyclic heat engine. The word cyclic is very important, so just keep in mind. This is a cyclic heat engine, and the process goes from B to C and then B to A are adiabatic and reversible. So we can say that a cyclic process may be called as a reversible process as well. Reversible process. So from this, we can conclude that it is a cyclic process. So cyclic process returns to its initial state. So the overall change in the internal energy and entropy is zero. So as we say that the cyclic process always returns to its initial state. So we can conclude from this that the change in internal energy and entropy is zero. So change in internal energy and entropy is zero. So we have this two points from the cyclic state. So if we look at the statements here, the statement says the net change in the internal energy of the gas in one cycle is zero. The total change in the entropy of the gas during the cyclic process is zero. So from this we can say that the statement number 1 and statement number 2 is correct. From the definition of the cyclic process, we can say that the net change in the internal energy of the gas is zero and the total change in entropy is also zero. So we don't have to look for the equation 3. As we can see in this process, the first option says option 1 only. So statement 1 is correct, but it does not mean only 1 is correct. So the option A is discarded. Second says the total change in the entropy of the gas is 0. So the total change in entropy of the gas will be 0, but it is not the only statement which is correct. So we will cross this as well. And from the definition of the cyclic process, we can say that the internal energy as well as entropy is 0. So C is the perfect choice, where you can see we have option 1 and 2 only. So the statement 1 says the net change in the internal energy of the one cycle is 0. We satisfied this statement of cyclic process, and the total change in the entropy of the gas during this cycle is also 0, which also satisfied the cyclic process definition. And the third option, why we did not choose the third option in this? Because during one full cycle, net work is done on the gas, which is incorrect. If we actually look at the curve, we understand, and it's a cyclic process and as well as a reversible process. So from this, we can conclude that the work done during the full cycle, so work is done by the gas. Work is not done on the gas. So work is done by the gas. So we can say that W net is greater than 0 in this case. In this case, we can say that the net work done is greater than 0. That's why we discarded option 3, because during the full cycle, the work is not done on gas. Work is done by gas. So the correct answer is 1 and 2 only. Hope you understood this numerical as well. Friends, we have one more numerical. So the pressure volume diagram below shows an adiabatic process from A to B. So from A to B, we have an adiabatic process and isovolumetric process from point B to point C. So from this, we have to determine which of the following is correct about change in internal energy of a process from A to B and B to C, from A to B and B to C. So we know that in adiabatic process, no heat energy is transferred. So we can assume that the work done is 0 in case of adiabatic process. Similarly, if we look at from point B to point C in the graph, we see that it is an isovolumetric process. It means volume is constant. And in the isovolumetric constant, no work is done and heat is removed in this process. So now we have this. So we will use two equations to solve this. So we have equation number 1, which says Q is equals to delta U plus W. What is Q? Q is heat energy. And what is delta U? Delta U is change in, uh, delta U is change in internal energy. And what is W? W is work done. Now we know we will be using one more formula, which is we know that P times V divided by T is equals to constant. We know that P is pressure. We know that V is volume and T is temperature. Now let's solve this equation. Let's solve this numerical step by step. So if we look at the process from A to B, so from A to B, we know that it is an adiabatic process. So if we know that in adiabatic process, no heat enters or leave the system. So from point A to B, we can say that Q is equals to 0 and work done will always be greater than 0. So the work done during the process is 0. So, sorry, work done is not 0. Work done is not 0. Work done and work is done on the from point A to B. So in the adiabatic process, heat energy is no heat energy transfer takes place, but the work is done. So it's not 0. So we know that the heat energy transfer is 0 and work done is always greater than 0 in case of an adiabatic process. So if we plug this data plug this data into our equation of heat energy, we can see that Q is equals to delta U plus W. So we know that Q is equals to 0. So we can write it as delta U is equals to minus W plus 0. So we can assume from this we understand that delta U is negative. So we have solved the first part, which says from point A to point B, which is the adiabatic process, and in which the heat energy transfer is 0 and work is done in this process. So we have concluded that delta U, that is the change in the internal energy from process A to B, will be negative. Now let's have a look at the second part. So the second part is an isovolumetric process. So in the volumetric process, we understand that the heat is removed in this process and no work is done in this process, right? So if we just plug this equation, that is Q is equals to delta U plus W, we get Q is equals to delta U. But we know that if we look, let me just rub it so you will understand. So from point B to C, we can see that the pressure is decreasing at constant volume. So the volume is constant, but the pressure is decreasing significantly. So we can say that heat energy is removed in this process. So we can say that Q is less than 0. So if Q is less than 0 and Q is equals to change in internal energy, so internal energy, that is delta U, must also be less than 0. So that's why delta U is negative in this process. So from this we understood that the change in internal energy of a gas of a gas in the adiabatic process, that is from A to B, and in the isovolumetric process, that is from B to C, is negative. So here only one option we have that we can see as negative. So that is option A. So from A to B it is negative, and from B to C also it is negative. So hope you understood and liked my numericals. So please like, share and subscribe to my channel. Thank you.
If this helped you understand physics better, like the video,